Hello everyone, welcome to the 27th lecture of the course Discrete-time Markov chains and Poisson processes. So in the last lecture we solved a couple of problems on exponential distributions where we used all the properties of exponential distributions. So today we will see another small thing which we will need in for Poisson processes. Remember, we are doing all these as preparation for Poisson processes. So before we can start Poisson processes, we will need one more thing which we will learn in today's lecture. And that thing is what is called order statistics. So what is order statistics? So let so it's a theorem. So let x1, x2 and so on up to xn be independent and identically distributed continuous random variables with probability density function small f. If we let xi denote the ith smallest of these random variables. So that means x1 is the smallest, x cap n is the maximum one, x2 is the second smallest, x3 is the third smallest and so on. So if we let xi denote the ith smallest of these random variables, so you have n IID continuous random variables. IID means independent and identically distributed with probability density function small f. Now if we let x with this suffix bracket I denote the ith smallest of these random variables. Now if I look at these collection x1 and so on up to x, so here it is now x bracket 1 and so on up to x bracket n, these are called the order statistics. So you are looking at from smallest to largest, right? So that's basically the definition of, so given n IID continuous random variables, what is the order statistics corresponding to that? If you basically order those random variables from smallest to largest, right? So now the theorem says that the joint probability density function, so now this is you can think of it as a random vector, this x bracket 1 and so on up to x bracket n. So the joint probability density function of this random vector, so this again will be a continuous random vector, is given by this formula. So what is it? So remember, you are looking at order statistics. So here this x1, x2, xn, so these are the variables. So obviously because x bracket 1, so x bracket 1 is less than x bracket 2 and so on, which is less than x bracket n. So these variables should also respect that ordering. So first of all, this is non-zero only when this x1 is less than x2 and so on less than xn, because the random variables has this relation between them. So if this is not true, then the probability density function or the joint probability density function is 0, and if this is true, then it is given by this quantity. Now we will not prove this theorem, but let me try to explain to you heuristically why you get this. Now suppose instead of xn, let me look at say x1, x2, x3. Now see, for any three values so if I suppose it takes x1, x2, x3. Now you can permute each of these values, right? But still when you order, so for example what I mean is, suppose if I give you 1, 2, 3 or 3, 2, 1 or 2, 1, 3. Now if so when you look at, so in this case this is x1, this is x2 and this is x3. In this case this is x1, this is x2, this is x3. Similarly this is x1, this is x2, this is x3. But if you look at x bracket 1, then this is. So what I am saying is, if I give you n numbers, now for all possible n factorial permutations of those n numbers, if I just order them, they will give me the same ordering. Just like this 1, 2, 3, 3, 2, 1, 2, 1, 3. So if I just look at it as a 3 tuple, then these are different. but if I just order take the numbers and order them, they will give me just one thing, right? 1, 2, 3. So if you are given n numbers, if you are looking at it, so if you are looking at, if you are doing permutations of them, and if you are looking at it as n tuples, then they are different. But if you are just ordering them, so all n factorial possible permutations of n numbers will give you the same ordering. That's important. That's why you get this n factorial, because see, when will these x1, x2, xn take these values little x1 up to little xn? So it doesn't, so for example, say if, as I said, say if x1 is 1 and x2 is 2, or x1 is 2 and x2 is 1, in both these cases your x1 is 1 and x2 is 2. Fine. So if you permute a set of numbers, its ordering doesn't change, right? Still, so among 1, 2, 3, the lowest is 1 and the highest is 3. Similarly, if I give you 2, 1, 3, still the lowest is 1 and the highest is 3. Yes, now the lowest one is the second random variable and the highest one is the third. So again, which one is the lowest, which one is the highest, that might change. But just if you look at the ordering, that doesn't change even if you permute the numbers. That's why all possible permutations, so since there are n numbers, so all possible permutations, or the number of possible permutations is n factorial. So you get this. And why do you get now? So see, that is the thing. So your random variables should take the values x1, x2 and so on xn, but you know that they are independent, so as well as identically distributed, having this density function. So the joint density becomes this product density. Fine. So the n factorial comes because even if you permute the numbers, still that will not change the order statistic. Just the example I gave, if x1 is 1 and x2 is 2, or if x1 is 2 and x2 is 1, in both these cases the order statistic is 1, x1 is 1 and x2 is 2. Fine. So corresponding to both these possibilities, you get the same order statistics, but here there are just 2 factorial is 2, but if you have n, then you get n, there are this n factorial possibilities which will give rise to the same order statistic, and from where this second term is coming, that is just independence and identically distributed. That's why you get this product of density of the marginal densities. Fine. So that's the heuristic explanation of this density. Again, if you have to prove it, the proof is slightly more complicated, but anyway, the heuristic should be clear. Fine. Okay. Let me just clean this a bit. Okay. Now, when you have a joint density, then you can calculate the marginal densities, right, just by integrating out the other variables. So doing that, again, we will not see the proof of that because the proof will be some slightly tedious calculation. Again, the proof is not difficult, like when you are given the marginal joint density, finding the marginal density, you know what you have to do. You have to just integrate out the remaining variables. But again, since here it's a but the integration can be complicated. So we will not do the integration here, but in principle you know how to find marginal density when you are given the joint density. So here this corollary is saying, so let x1, x2, xn be IID continuous random variables with probability density function f dot and cumulative distribution function capital F dot, then the marginal of the ith order statistic. So we are looking at x bracket I, so the marginal of the ith order, or the marginal density of the ith order statistic is given by this quantity. Fine. So again, although we will not see a proof of this, but let us see. So again, this will be true for where all these things are positive. Fine. Okay. Now again, let us try to see if we can understand heuristically from where this density is coming. Now, if the ith minimum is x, so remember the ith minimum is x, that means below that there are I minus 1 numbers, and after that there are n minus I. Remember, there are total n numbers. You are told that x is the ith minimum, that means there are I minus 1 numbers below it and n minus I numbers after it. Fine. So that you see. So again, this is fx is coming because of this, that the ith one is x. Now this capital Fx I minus 1 comes from the fact that there are I minus 1 below x. Remember, what is fx? Fx, or let me write it here. So fx is probability x less than or equal to x. So this fi to the x to the power I minus 1, remember here these are all independent and identically distributed, so it becomes just the product. So basically it tells you that I things should be less than x, and that probability is given by that I minus 1 things should be less than x, so that is fx to the I minus 1. Again, it becomes this, goes to the power because of independent and identically distributed, and n minus I should be greater than that, that is 1 minus fx, because 1 minus fx is probability x greater than x. So n minus 1 I things should be greater than x. That's when I will be the x will be the ith minimum if I minus 1 is less than that and n minus I is greater than that. Now, so basically what you are doing here, so again, so x will be the ith minimum when I minus 1 things are less than that and n minus I things are greater than that. But again, remember, in terms of the original random variables, you can permute things, right? And but still you will get the same order statistic. So basically what? You have to choose which I minus 1 will be less than, which n minus I will be greater than, and which one will be the ith minimum, right? So basically from n people you are making 3 groups. A group which will be this I minus 1 minimum, that will contain I minus 1 things. Then which one will be the ith minimum, that's a group of 1, and then a group of n minus I which will be greater than x. So the number of ways you can group n people in these 3 groups, one group containing I minus 1, one group containing 1, and the other group containing n minus I. So what you are doing, you are given say n things, you need to group among them, you need to choose a group of n minus I minus 1, and 1 which will be the ith minimum, right? So first you choose say I minus 1, give them values. So for any possible values of them which is less than x, you give them values less than x. Now n minus I, you give them values greater than x, right? So now you can give any values to this n minus I minus 1 as long as one is less than x and the other is greater than x. So basically you are given n numbers, you have to make them divide them into 3 groups, fine. The ith one should be x, I minus 1 should be less than that, and n minus I should be greater than that. In how many ways you can do such thing? That thing you can do in these many ways. N factorial over n minus I factorial times I minus 1 factorial, right? For all such groupings, you will get that the ith minimum is x, I minus 1 is less than x, and n minus I is greater than x. So basically you have to choose which one will be less than among the first I minus 1 and which one will be in the later n minus I. So and how many ways, given n things, how many ways can you form such groups? Again, that's just permutation combination, it is just n factorial divided by n minus I factorial times I minus 1 factorial, right? that gives you this density. So again, this is not a mathematical proof, but I have tried to give you a heuristic understanding of this density. So if x has to be the ith minimum, then I minus 1 has to be less than that, n minus I has to be greater than that. And again, so since order statistic does not change on permuting, so you can get this in multiple ways. In how many ways? So given n things, you have to choose which I you want to give value, I minus 1 you want to give values less than x, and which n minus I you want to give values greater than x, right? And that can be done in these many ways. That grouping can be done in n factorial divided by n minus I factorial times I minus 1 factorial ways. Fine. So that gives rise to this density. But again, if you have to do it mathematically, you will have to just do it from this joint density by integrating out the other variables, but that integration is slightly complicated. So I have not worked out that thing in this lecture, but again, heuristically this density should make sense, right? So this slide gives you what is the joint PDF of the order statistic given n IID continuous random variables with a common probability density function small f, and also it gives you the marginal density of the ith order statistic. Fine. Okay, now let us see an example. So let x1 and x2 be two independent exponential random variables, each having parameter lambda. Find expectation of x2 and variance of x2, right? So we will use the previous thing. Now, so basically we get from this corollary that the PDF of x2 is given by this. Fine, that's easy to see just using this formula. Fine. Now, once I have the density, now I can calculate the mean and the variance. So to find the mean, we just integrate this from 0 to infinity, integrate the density from 0 to infinity multiplied by x. Now I just separate it, so this and this, but now remember, if you take this 2 outside, this is just integration 0 to infinity x lambda e to the power minus lambda x dx, that is nothing but just mean of an exponential random variable with parameter lambda, so that is 1 over lambda, but since you have this 2, you get 2 over lambda. And now if you look at this integral, this is just the, so 2 lambda e to the power minus 2 lambda x, that is just the density or the probability density function of an exponential distribution with parameter 2 lambda, and so here you are just calculating mean of that. So the mean of that will be just 1 over 2 lambda. So you get 2 over lambda minus 1 over 2 lambda equal to 3 over 2 lambda. So again, this integration you can easily do, but what I am saying is that since you know what is the mean of exponential distribution with a given parameter, you don't even have to do these integrations, work out these integrations explicitly. If you remember that, then you can straight away just write down these things. Fine. Okay, so that's the mean. So here x2 is since here it's just 2 random variables, so it's x2 is basically max of x1 and x2. So you are trying to find the maximum expectation of maximum of 2 independent exponential random variables, each having parameter lambda. So you already know what is minimum. For minimum, we already know that minimum of 2 exponential random variables is again exponential with parameter, just sum of the parameters. So here again, here we are not exactly finding the distribution, but again, so we actually have found the distribution because this is the density of the maximum. So you can, so that gives you the distribution of the maximum, and also we have calculated the mean of the maximum. Now what about the variance? Now before finding the variance, we first find the second moment. So again, we need to calculate this because the density is what is given in the previous slide. Now again, we will use, so if x is exp lambda, then expectation of x square is given by 2 over lambda square. Again, this you can easily check, so we will use it here. So again we break the integral. Now the first one again, so 2 we can take out, this 2, and then it is just x square lambda e to the power minus lambda x dx. So this is just expectation of x square for where x is exponential lambda. So that will give you 2, this 2 is already there, 2 times 2 over lambda square, that gives you 4 over lambda square, and this is expectation of x square where x is exp 2 lambda, right. Now I look at this density, 2 lambda times e to the power minus 2 lambda x times x square, fine. So now it is just expectation of x square where x has this distribution. So now we get just 2 times, so this is nothing, so this is basically 2 over 4 lambda square, because it will be 2 over the parameter square. So here the parameter is 2 lambda, so we get 1 by 2 lambda square. Now if you do this, you get 7 by 2 lambda square. So the variance is expectation of x square minus expectation x the whole square, or expectation of this x2 whole square minus expectation of x2 the whole square. We already know from the previous slide what expectation of x2 is. So finally we get that this is the variance, right. So using this theorem in the first slide, we get this mean and variance of maximum of 2 independent and identically distributed exponential random variables with parameter lambda, right. But now we already have seen that exponential random variables are somewhat spatial. Now it turns out, like, again, this is the general method. The first method that we worked out is the general method. So instead of exponential, if it was some other random variable, then we would have followed this method, which we did first. But now we know that exponential random variables are somewhat special. It has some very special properties, one of them being this memoryless property. Now it turns out, because of that, this particular problem for exponential random variables can be done in a slightly easier way, because here you see you need to do all these integrations. So if here I use those facts, mean of exponential, the second moment of exponential, but if you don't remember all those things, you'll have to work out all these integrals. But since the random variables are exponentially distributed, the problem can be done in a simplified manner. So again, that is because it is exponential. Instead of exponential, if it was something else, then the first method, the way we calculated, that's the way to do it. But since exponential is special, so, and the problem is for exponential random variables, we give a second method, which you will see is a much simpler method to calculate mean and variance. Remember, because we are just interested in mean and variance, fine. So the other method also gave us the distribution, because it gave us the probability density function. But since we are just interested in mean and variance, the problem asks you just about the mean and variance, and the random variables are exponential, you can do it in a simpler way. What is that simpler way? So now by memoryless property, x1 and x2 minus x1 are independent exponential random variables with parameters 2 lambda and lambda respectively. Why is that? Because what is this x2 minus x1? That is just simply like the remaining. So, x1 tells you x1 is basically the minimum of 2 exponentials, right? So that you know that has to be again an exponential random variable with parameter 2 lambda. But now the claim is this x2 minus x1 and x1 is again independent. Why? Because this x2 minus x1 is, you can think of it as the excess life, right? So how much bigger this x2 will be in comparison to x1. So what is the difference? So it is again looking at the excess life or the remaining life, right? So that we know by memoryless property that how much more it will be again does not depend on what you are already given, that you are already given that okay, it is at least this, how much more it can be. Now for that, what it is at least is not important, only thing is how much more it can be. So that is x2 minus x1. So but by the memoryless property, that will be just simply exponential. That is because, again, we have seen this argument before, that the remaining, like we saw in the previous lecture, that this remaining service time is just the original service time, right, because of this memoryless property. So here is the same thing. So if you think of this x1, that is the service time of the x bracket 1 is the service time of the first customer, and who to leave, and this x bracket 2 minus x bracket 1 is just the remaining time, service time of the customer who is still in service when the first customer, the customer who leaves first leaves. So this again is exponential with the original parameter, and also these are independent. So x1 and x2 minus x1 are independent exponential random variables with parameters 2 lambda and lambda respectively. That x1, the parameter has changed because now you know that x1, this is basically minimum of two exponentials, and the parameters are lambda and lambda. So when you add lambda plus lambda, you get 2 lambda, and this x2 minus x1, that it is independent of x1, x bracket 1, and it is again exponential lambda, that is because of memoryless property. So if you have to find the expectation, then expectation of x2, you can just simply write it in this way. Now expectation is just linear, so expectation of x1, since it is exponential with parameter 2 lambda, so its mean is 1 over 2 lambda, and expectation of x2 minus x1, since it is exponential with mean lambda, so it is 1 over lambda, and you get this 3 over 2 lambda, which is the same answer that you got here. Fine. Obviously you should get the same answer because you are working out the same problem in two different methods. So here we basically didn't need the independence of x1 and x2 minus x1 because expectation is linear, but when we want to calculate variance, again we break it in this way. Now we know that variance of, if you have given two random variables x plus y, the formula is variance of x plus variance of y plus covariance of xy. But in this case, since it is independent, so this covariance term will not come, because you know that if two random variables are independent, then covariance of xy is 0, or in other words, they are what is called uncorrelated. Fine. So this covariance term will not be there, so this will be 0. So to calculate the variance, we are using the fact that they are independent. So variance of this plus this will be just variance of this x bracket 1 plus variance of x bracket 2 minus x bracket 1. But again, what is variance of x bracket 1? We know that if you have exp lambda, then variance is 1 over lambda square. Again, you can calculate that. So if x has exponential lambda distribution, then variance of x is 1 over lambda square. So since x1 is exponential with parameter 2 lambda, so its variance is 1 over 4 lambda square. And what is variance of x2, x bracket 2 minus x bracket 1? That is just exponential lambda, so it is just 1 over lambda square. Again, if you do the summation, you get 5 over 4 lambda square, again the same thing that you got by the previous method, right? So you see, since the given problem is for exponential random variables, you can do it in a much simpler way without using those theorems or corollary on order statistics. That is because these are exponential random variables which has this spatial property of memoryless. That exponential random variables have this memoryless property, right? So, and since you again remember the previous method also gave you the PDF, because from that corollary you get the PDF of the maximum as well, but this method you don't get the PDF. But what you again you can, because you remember now you know that x1 is what? X1, so again, so although I say that you cannot get the PDF, I have not worked out the PDF here, but just let me tell you, even in this method also you can get PDF. Why? Because you know this x bracket 2, you can write it as x bracket 1 plus x bracket 2 minus x bracket 1. Now x bracket 2, x bracket 1 and x bracket 2 minus x bracket 1, these are independent random variables. Fine. Both are continuous random variables, have certain density. You remember this, you know that if x and y are two independent continuous random variables, having density functions f and g, then you have this convolution formula. So, the density is actually given by integration 0 to infinity f of x minus y gy dy. So, that is say the density of the sum, provided x and y are independent. So, here again, since you can write x bracket 2 as x bracket 1 plus x bracket 2 minus x bracket 1, x bracket 1 is exponential with parameter 2 lambda, x bracket 2 minus x bracket 1 is exponential with parameter lambda, and these are independent. So, you can use the convolution formula. So, you can try it out as an exercise using the convolution formula, find the density of x bracket 2, and you should end up with this formula. Fine. So, the convolution formula should give you this density. Fine. So, although in this example I have just worked out the mean and the variance, you can, using this all these properties of exponential, you can also find out the density of maximum of 2 exponential using this convolution formula. Fine. But again, since the main thing was just the question asked about mean and variance, so we can calculate it very simply for, because here the given random variables are exponential. But if it is any random variable, then the first method which we employed is the one to use, right? But since exponential is special, there is an easier way to find out the answers that you are looking for. Fine. Okay. So, we have worked out the problem in 2 different methods. Obviously, we have got the same answer, we should get that, but here there are 2 different methods because we are working with, or the problem is about exponential random variables, right. So, now we have finished all the prerequisites for Poisson processes. So, in the next lecture, we will start with Poisson process. Okay. So, we will stop here today. Thank you all.